welcome back again to my channel. So today we are going to learn about a new topic which is dimension reduction. So let's start. Dimension reduction is a process used to decrease the number of input variables or features in a dataset while preserving as much relevant information as possible. This technique addresses challenges associated with high dimensional data such as overfitting, increased computational complexity and difficulties in visualization. So this method can be categorized into two types: feature selection and feature extraction. Feature selection, it involves identifying and retaining the most relevant features from original dataset. And common methods include statistical test, recursive feature elimination (RFE), and regularization techniques like lasso. Then we have feature extraction, which is transforming the original features into smaller set of new features by combining or projecting them. Popular techniques are PCA, which is principal component analysis, which identify new orthogonal axes that maximize variance in data, effectively summarizing dataset. Then we have linear discriminant analysis (LDA), which focuses on maximizing class separability, making it particularly useful for supervised classification problems. Then dimension reduction is widely applied in fields like bioinformatics, image processing, and finance, where data sets often in thousands of features and they contain it. So it enhances model performance, reduces noise, simplifies interpretation, and careful attention is required to ensure that reduced data set retains sufficient information for meaningful analysis and accurate predictions. So to demonstrate how you will handle multi-collinearity in Python. So it basically arises when two or more independent variables in regression model are highly correlated, making it challenging to assess the individual effect on dependent variables. So this can lead to unstable coefficient estimates and reduce the interpretability of the model. We can detect multicollinearity using the following method. First is correlation matrix, which examines pairwise correlations between features, and then we have variance inflation factor (VIF), which measures how much a predictor is linearly explained by other predictors. So for this, here's an example. First, we will import all the libraries such as pandas, numpy, cpon, matplotlib, stats model. Then we will enter the sample dataset. Then we'll convert it to data frames. Right? Then I will add that correlation matrix. Then I will visualize that correlation matrix. Then we will do the variance inflation factor (VIF). Then we'll display it. So the key steps that are correlation matrix that computes pairwise correlations between independent variables, and above 0.8 to 0.9 suggests potential multicollinearity. A heat map provides a visual representation of correlations. Then we have variance inflation factor (VIF). It measures how much a predictor's variance is inflated due to multicollinearity with other predictors. Okay. So if value is less than 5, no multicollinearity concern. If it is greater than 5, moderate multicollinearity, and if it is greater than 10, then it is severe multicollinearity. Upward interpretation correlation metric identifies highly correlated pairs of variables like x1, x1, and x2, x2. Then VIF table, it lists each features with its VIF value to highlight predictors contributing to multicollinearity. Okay, then I will demonstrate how you will apply principal component analysis. So PCA, it is basically a dimensional reduction technique that transforms high dimensional data into a lower dimensional space while retaining maximum variance. Here's how you can use it. First, we'll import all the libraries, then we will enter sample dataset, then standardizing and data, then we will apply PCA, then we will explain the variance ratio, visualize it, then display it. So steps of code are that standardizing data. Firstly, we will PCA. It is very sensitive to variable scales, so we will use standard scaler to standardize all features and ensure equal contributions to the analysis. We'll apply PCA. Initialize PCA with n components equal to k to specify number of principal components to retain. Then we'll use fit transform method to compute and transform data. Then we will analyze explained variance, which will be improvise the proportion of total variance captured by each principal component. Then we will visualize that results, which is that plot the transform data points into new principal component space for clear view of patterns or clusters. So output interpretation. First in principal components. Resulting principal components represent data in reduced space. Explained variance ratio, it indicates percent of total variance explained by each component. And components with higher variance ratios are more important. Visualization, the scatter dot displays data points reduced dimensionally, providing insights into clustering or spread. Then why to use PCA? It is useful for reducing dimensionality in grid sets with many features, improving computational efficiency, reducing noise, and simplifying visualization while retaining most of the original data's variability. So this was all for today, and thank you so much for patiently listening and watching. Thank you.